All right, welcome on in. So today we're going to be starting chapter 9. We only have 3 sections left to cover. Today we'll cover section 9.1, and we'll talk about the take-home assignments. We don't have any class Thursday, so I hope you have a happy, healthy, safe Thanksgiving. We got a nice break there. Next week is the last week of class. So Tuesday will be section 9.2. Thursday will be section 9.4. I've been trying to even out the pace here at the end, so you have plenty of time to get everything done. You've got assignment 13, quiz 13 due this Wednesday. Next Wednesday, you've got assignment 14, quiz 14. And then finals week, we won't have any class finals week. I'll just have an office hour for each class. And you've got assignment 15, quiz 15, your project, and then the final assignment. And so after today, you'll actually have everything you need to work on your final assignment. So you should be well prepared to finish everything up here in these next couple weeks. So a sequence, there's a couple different ways to think of a sequence. Informally, a sequence is just a list of numbers. All right. So here's how we start a sequence: 1/2, -3/4, 9/8, -27/16, etc. And these periods of ellipsis are kind of dangerous because whoever starts writing the sequence is just going to assume that you're going to continue the pattern in the way they think it should continue. Something we did in Math Club earlier this semester is we proved that really any number could follow that and still have a quote-unquote legitimate sequence behind it. But we can try to look for some patterns here. We've got a 1, 3, 9, 27. So in the numerator, it looks like we're multiplying by 3 each time. In the denominator, it looks like we're multiplying by 2 each time. And we have a pattern of a plus, minus, plus, minus. So, the goal of today is to look at sequences and look at some particular types in order for us to get some formulas for some of the more common sequences. So each of the numbers in the sequence is called the term of a sequence, and that might be a little confusing because normally in mathematics when we talk of the word term we mean addition, and that's kind of a spoiler for what we're going to be doing with sequences next week, is we'll be adding things up. So 1/2 is called the first term, second term, third term, etc. And so this is how we get functions involved because, with the exception of chapter 7, we really haven't been studying functions. The things in chapter 7, well, they could be modeled by more than one function if we solved for the right variable, but the big concept in college algebra is always the concept of function. So we can actually make a function here and match up the natural number n with the term a sub n. So we can think of this first term, second term, third term as matching the number 1 up with 1/2, 2 goes to -3/4, etc. Okay. So instead of having a function, like we've done before, like f of x equals 2x plus 1, where x can take on any real number. So x could be a whole number like 3, or x could be some crazy irrational number like -√2. What we're going to be looking at here is looking at our domain being this discrete set of numbers, these natural numbers. So instead of calling it a of n equals whatever, say 2n plus 1, when we use the letter n here, we're thinking of n being these whole numbers. Okay, so a of 2 would be 2 times 2 plus 1, which would be 5. Instead of calling it a of n, we usually write it as a sub n. So this is kind of a modified function notation. When you see a sub 2, it means to plug in n equals 2. So we would get 5 in that case. So that's kind of how functions get involved with sequences. So let's practice this new kind of function notation here. Write out the first 4 terms of the following sequence. So once again, when you see the letter n here in chapter 9, we're assuming it takes on these whole number values. Here we're told that n starts at 1, so a sub 1 means everywhere I see an n, I'm going to substitute in a 1. So it'd be 5 to the 1 minus 1 power over 3 to the first power. So 5 to the 0 over 3. 5 to the 0 is 1, 1/3. A sub 2 would be 5 to the 2 minus 1 over 3 to the 2 power. That's 5 to the first power over 9, which is 5 over 9. A3 means to plug in n equals 3. So I'd have 5 squared over 27, which is 25 over 27. And then to get the 4th term, a sub 4, plug in n equals 4. So that would be 5 cubed over 81, which is 125 over 81. The dog has a new toy, so he's playing with that. All right. So the first 4 terms of the sequence are a third, 5/9, 25/7, a 25/81. So you'd write the sequence out this way. And then, of course, you put the dot, dot, dots. If we try to see the pattern here, the numerator, we're constantly multiplying by 5. The denominator, we're multiplying by 3. Okay, so that's the pattern. All right, so you want to think of this as like a modified function notation. All right, number 2, we've got b sub k. So we're using a different letter here. Instead of n, we're using k. And here we're told that k starts at 0. So once again, we still are going to have these whole number increments to get started here. So b sub 0 means everywhere you see a k, we're going to plug in a 0. So that would be a 1 over 1. And so that would be a 1. B sub 1 means everywhere we see a k, we plug in a 1. So that would be a negative 1 over 3. B sub 2 means everywhere we see a k, we plug in a 2. So that would be a positive 1 over 5. B sub 3, everywhere we see a k, plug in a 3. And so those are the first 4 terms of the sequence. Since we started at 0, I only go up through k equal 3. And here's our list of numbers. Okay. Now if I look at a pattern here, notice the numerator is either 1 or negative 1. It's alternating back and forth between plus or minus 1. And what's causing that to happen is because we got negative 1 to a power. And so anytime you have a negative 1 to an even exponent, it's a positive 1. A negative 1 to an odd exponent, it's a negative 1. And the denominator, we're getting all the odd numbers, 1, 3, 5, 7, 9. We start at 1 and then we add 2 each time. Okay. So once again, we're going to, in just a few minutes, we're going to dive a little deeper into these patterns. So if we see a pattern like that, we'll be able to get a formula for it. Any questions on this example? Do you kind of see what's happening here with this notation? All right, number 3 is a different way to express a sequence. It's expressing the sequence as a set of numbers. So that's what those set braces are. It tells us to start at n equals 1, and then the n equals infinity just means that it continues on. So starting at n equals 1, we've got right here, 2 times 1 minus 1, which is 1. N equals 2. 2 times 2 minus 1, which is 3. N equals 3. 2 times 3 minus 1, which is 5. N equals 4. 2 times 4 minus 1 equals 7. And so there's the first 4 terms of the sequence here. Excuse me. And once again, notice we're getting the odd numbers again, right? So, you could have different looking formulas generate the same list of numbers. So these are the same numbers we had in the denominator of number 2, but because of where the k started, we're using a different formula. So that's something that we're going to talk about here in a little bit. Number 4 is an interesting one. So once again, it's starting off, here we're using I as the index or the counter here. So this is different than the square root of negative 1. Here we're starting I goes from 2 to infinity. 1 plus negative 1 to the I power over I. So let's start off here with I equals 2. It would be 1 plus negative 1 squared over 2. Negative 1 squared is positive 1. Plus 1 is 2. 2 over 2 is 1. When I equals 3, we've got 1 plus negative 1 cubed over 3. So we got 1 minus 1 over 3. That's 0 over 3, which is 0. I equals 4. 1 plus negative 1 to the 4th over 4. Negative 1 to the 4th is a positive 1. So I get 2 over 4, which is a half. And then the 4th term here, I equals 5. 1 plus negative 1 to the 5th over 5. Be 1 minus 1 over 5. 0 over 5, which is 0. Okay? And so the first 4 terms of the sequence are 1, 0, 1/2, 0. And even though you get 0 out, zeros count as terms of the sequence. Okay, zeros count as terms of the sequence. And so once again, we see that negative 1 to a power switching between plus 1 and minus 1, and that's what essentially is killing off half the terms there, zeroing them out. All right. Now, since with sequences we're always moving in whole number steps, this allows us to describe sequences in a different way. So these first 4 examples are examples of what's called an explicit formula for the sequence, because it tells you whatever your counter is, it tells you exactly what you do. You plug it in and you're done. Another way to describe sequences is recursive definition. So recursive definition is kind of like climbing a ladder. In a recursive definition, it's going to tell you where to start. And then it's going to tell you how to go to the next. So you're climbing a ladder, you get on the first rung there, and then the way you climb the ladder is once you're on a rung, you step up to the next rung. Then you get to the second rung, and then you step up to the third rung, etc. Okay? So that's the idea here, is with the recursive sequence, it tells you where to start. And then it tells you how to go from one to the next. All right. So we're going to work through this example on a blank slide here. So A1 is 7. It tells us A1 is 7. So this is where we're going to start. And then how do we go from one to the next? A sub n plus 1. So notice this is down here in the subscript, A sub n plus 1. So how do I get to the next one? It says you take 2 minus A sub n. And then this formula is good for n bigger than or equal to 1. So this is called the recursive formula, or the recursion equation. It tells you how to go from one to the next. So let's look at this recursion equation, and let's start off by doing n equals 1. So if I plug n equals 1 into this recursion equation, I would have a sub 1 plus 1 is equal to 2 minus a sub 1. In other words, a sub 2 is 2 minus a sub 1. Where do I get a sub 1? Well, they told us that a sub 1 is 7, so that goes in here. So 2 minus 7, and I get negative 5. So a sub 2 is negative 5. N equals 2 into the recursion equation. A sub 2 plus 1 is equal to 2 minus a sub 2. In other words, a sub 3 is 2 minus a sub 2. Where's a sub 2? 2 minus negative 5. A sub 2, or a sub 3 rather, is 7. And one last one here to get to the fourth term. N equals 3. A sub 3 plus 1 is 2 minus a sub 3. In other words, a sub 4 is 2 minus a sub 3. A sub 3 is 7. 2 minus 7, negative 5. So a sub 4 is negative 5. So this sequence generates the number 7, negative 5, 7, negative 5, and so on. So it just flips back and forth between the two. So the way I think about this, and this is eventually the way you want to get to with recursive. I mean, initially you want to go through, excuse me, spell out each of the steps, but if you try to take a big picture here, we're starting with 7, and the way we're getting to the next one is taking 2 minus the one we have. So I start with 7, 2 minus 7 is negative 5. To get to the next one, I take 2 minus negative 5, that gets me to 7. To get to the next one, 2 minus 7, negative 5, and so on and so forth. Any questions on this first example of a recursion? All right, let's look at this one. This turns out this is a famous sequence. F sub 0 is 1. F sub n is n times f sub n minus 1. So f sub 0 is 1. F sub n is n times f sub n minus 1 for n bigger than or equal to 1. So let's start off with this sequence. Looking at the recursion equation, f sub 1 would be 1 times f sub n 1 minus 1, which is 1 times f sub 0. F sub 0 is 1, and so f sub 1 is 1. So far it's not very exciting. F sub 2 is 2 times f sub 2 minus 1, which would be 2 times f sub 1, which we just calculated was 1. F sub 3 would be 3 times f sub 3 minus 1, which would be 3 times f sub 2. And what's f sub 2? It's 3 times 2, 6. F sub 4. And at this point, we would be done, but I want to keep going because I want to show you what's actually happening here. F sub 4 is 4 times s sub 4 minus 1, which is 4 times f sub 3. And I know here f sub 3 is 6, so it's 4 times 6, which is 24. But let's write out a little more detail here. Let's use this step. So 3 times f sub 2 is 3 times 2 times 1, and that's another way to get 6. 4 times f sub 3 would be 4 times 3 times 2 times 1. That's another way to get 24. And hopefully now you can kind of see the pattern a little bit better. F sub 5 would be 5 times f sub 4, which would be 5 times 4 times 3 times 2 times 1, and that's 120. Okay? So this sequence is actually a very famous sequence, and it's going to get a lot of mileage for us next week. This is called the factorial sequence. So f sub n, this is called the factorial sequence. And it's usually denoted by n with an exclamation point. So n, right? Because you're excited about it. So written with this notation, 0 factorial is defined to be 1. 1 factorial is 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1, etc. In general, n factorial, the way you could describe it sort of explicitly, is n times all the numbers that go before it until you get down to 1. With the exception being 0 factorial starts you off at 1. Now, what is n factorial good for? All right. Well, I know some of you have had statistics. When I reviewed the get to know you sheets, a lot of you have had statistics. You may recognize n factorial in some probability counting type things. And this is what we'll get into the last day of class. We'll talk more about this. But let's say you had 5 different songs, and you wanted to know the number of playlists you could create with those songs. So a playlist, is just an ordering of those songs. So you could start off, and for you got 5 slots here for the 5 songs. So for the first choice, you have 5 different songs you can choose from. For the second slot, you now have 4 choices because you've picked one for the first slot. You got 3 choices for the third, 2 choices for the fourth, and then once you pick the 4 songs, the 5th song is already determined. So altogether, you would multiply 5 times 4 times 3 times 2 times 1. That'd give you 120 playlists. Okay? So that's what factorials are good for. They're good for counting ordered arrangements. So n factorial tells you the number of ways to order n things. All right? Number of ways to order n things. And we'll come back to this, like I said, a week from Thursday. Last day of class, we're going to come back to this kind of thing. Excuse me. But if you've had statistics, you may recognize this as permutations. You might have heard that word before. Anyway, it's a big deal. It's a big deal. And, based on, I know that there's a fair number of you that this is it for you in your mathematical career. If you went on to take calculus or more advanced statistics and things, factorials are huge. All right, factorials are huge. Now, there's another sequence, a famous sequence that's a recursion sequence. And if you want a couple extra points You can research this sequence. It's a Fibonacci sequence. All right. And you can see how that's a recursive sequence. It's actually in the book we talk about it. You can just look it up in the book. Look up the Fibonacci sequence, give the recursive definition for it, write out the first couple of terms. I'll give you a couple extra points for that. All right, let's talk about two basic types of sequences. And these tie back to two basic types of functions. All right. So the first type of sequence we call is an arithmetic sequence. So arithmetic sequence. Here's what an arithmetic sequence is. The way you go from one to the next is you're always adding or subtracting the same number. All right. So if we start off with a number, let's say 5, and let's say we're always going to subtract 2. This would be an arithmetic sequence because we're always adding, in this case, -2 to go from one to the next. So in general, an arithmetic sequence, you start with some number a, and the way you go from one to the next is you're always adding the same number. And so on. So there's a couple different ways to describe this. You can describe this recursively. A1 is A sub n plus 1 is A sub n plus D for n bigger than or equal to 1. So you're starting at A, and then the way you go from one to the next is you add D. Or you could look at it explicitly. A sub n equals, well, let's look. You start with A, so our A sub 1 is A. A sub 2 would be A plus 1D. A sub 3 would be A plus 2Ds, and so on. So A sub n would be A plus n minus 1Ds for n bigger than or equal to 1. So here's the other way to describe the arithmetic sequence. The D here, the reason this is called D, is this is called the common difference. All right? Because if you take the difference of any two successive terms, you get the same number. 3 minus 5 is -2. 1 minus 3 is -2. -1 minus 1 is -2. -3 minus 1 is -2, etc. Now, for every step, we're adding the same thing each time. Arithmetic sequences, well, we'll reveal that here in a minute. Let's do an example here. Let's just make one up here. Let's start with 3, and then 8, and then 13, and then 18, and then 23, etc. All right. So if we look here, the way we're going from one to the next is we're always doing what? We're always adding 5. Okay? That means it's arithmetic. The A here, what I'm starting with is 3. The common difference here is 5. Once again, 8 minus 3 is 5. 13 minus 8 is 5. 18 minus 13 is 5. 23 minus 18 is 5. And so I can put this together with my formula. A sub n equals a plus n minus 1d for n bigger than or equal to 1. A sub n is 3 plus n minus 1 times 5. And if we simplify this for a sub n, we're going to get 5n minus 5 plus 3, so 5n minus 2. So this would be a formula that would produce this sequence. There we go. Now, what's the best way to check your answer? When in doubt, write it out. So if we start here with n equals 1, I plug in n equals 1, 5 times 1 minus 2. Sure enough, that gives me a 3. If I plug in n equals 2, 10 minus 2 is 8. N equals 3. 15 minus 2 is 13. N equals 4. 20 minus 2 is 18. N equals 5. 25 minus 2 is 23. Boom. That's how you check your answer. Okay? Now, if you think about this back in function land, so if we kind of go back here and look at this as an f of x and use the variable x instead of n, you'll notice that this is a linear equation. Okay? So going way back to chapter 1, so it's like the third day of class, we talked about linear functions. Linear functions all have the form mx plus b. They have a constant rate of change. For every 1 over, you go up m. In this case, if I look at the slope here, is 5. Think of that as 5 over 1. That means for every 1 I go over to the right, I'm going to go up 5. So what does that sound like? That's exactly the concept of common difference. We move over 1 space, we're adding 5 each time. Okay? And so that's the thing that kind of ties this back into what we did earlier, is that arithmetic sequences are just linear functions. Where the common difference is the slope. Okay? Now, the other big class of sequence we're going to talk about is geometric sequence. Now, arithmetic sequence, the way you go from one to the next is you're always adding the same number. You have a common difference in play. For geometric sequence, you have a common ratio in play. So, an example of a of a geometric sequence, it would be 8, -4, +2, -1, 1/2, -1/4, etc. And if you look at what's happening, the way we're going from one to the next is we're always multiplying by -1/2. Another way to say that is that if you take the ratio of the adjacent terms, -4 divided by 8 is -1/2, 2 divided by -4 is -1/2, -1 divided by 2 is -1/2. The ratio of the adjacent terms is always the same. And that's what a geometric sequence is. A geometric sequence, you start off with some number a, and the way you go from one to the next is you always multiply by the same number. So recursively, A1 is some number A, And the way you get to the next number, a sub n plus 1, is r times a sub n. You multiply by r. The explicit formula for a geometric sequence, a sub 1 equals, well, let's look. a1 is a2 is a times r, a3 would be ar squared, a4 is ar cubed. So notice the number here is 1 more than what the exponent is. So a sub n would be ar to the n minus 1 for n bigger than or equal to 1. So that would be the explicit formulation for a geometric sequence. And you can kind of see what a geometric sequence is just from this without doing any more. Geometric sequences are exponential functions. Right. For example, if we wanted to get a formula for this sequence here, we're starting off here with a equals 8. The r is negative 1/2. So the formula would be a sub n is equal to a times r to the n minus 1 for n bigger than or equal to 1. And we can use some properties here of exponents. I've got 8 times a negative 1 to the n minus 1 over 2 to the n minus 1. 8 is a power of 2, so I could write that as 2 cubed. And finally, I could use properties of exponents. So I've got the 2 cubed there. So I could subtract. It'd be 2 to the 3 minus n minus 1 times negative 1 to the n minus 1. So it'd be 2 to the 3 minus n plus 1, so 4 minus n, negative 1 to the n minus 1. And so once again, you've got numbers to powers, and that's exponential. Okay. So let's practice recognizing arithmetic and geometric. On these examples here. So determine if the following sequences are arithmetic, geometric, or neither. If arithmetic, find the common difference d. If geometric, find the common ratio r. Okay, so the mantra in this chapter is when in doubt, write it out. So let's write out a few of the terms here. We've got a sub n is 5 to the n minus 1 over 3 to the n. For n bigger than or equal to 1. Now, based on what we just talked about, you've got numbers to powers. So we would suspect this is geometric. So let's write out a few terms and see if that bears out our assumption here. A sub 1, everywhere I see an n, I'll put in a 1. And that's 1/3. A sub 2, that's 5/9. You might recognize this sequence from about a half an hour ago. This is one of the same ones we had a half an hour ago. All right, so there it is again. Once again, we looked at this one a little bit ago. So here's our sequence: 1/3, 5/9, 25/27, 125 over 81. And let's see if this looks like a geometric sequence. It looks like it should be based on the formula here. So we need to look at the ratio, see if there's a common ratio here. How am I going from one to the next each time? Well, if I look at the numerator, I'm always multiplying by what? 5. If I look at the denominator, I'm always multiplying by what? 3. So in fact, I'm always multiplying each term by 5/3. And that's our common ratio. Now, if you actually wanted to prove it beyond a shadow of a doubt, because to be fair, we've only listed out 4 terms here, and there's infinitely many terms in the sequence. If we wanted to prove this, we have to look at a sub n plus 1 divided by a sub n. So let's do that. So a sub n is 5 to the n minus 1 over 3 to the n. And so a sub n plus 1, everywhere I see an n, I plug in an n plus 1. So that would give me 5 to the n over 3 to the n plus 1. So here's the nth term. Here's the n plus first term. Okay, so I'm looking at generically what's going on here. And now let's take those ratio, right? So that ratio would be 5 to the n over 3 to the n plus 1 divided by 5 to the n minus 1 over 3 to the n. So now we're going to go through our usual fraction gymnastics. 5 to the n over 3 to the n plus 1 times the reciprocal 3 to the n over 5 to the n minus 1. And so let's group together here what goes together. I've got a 5 to the n over 5 to the n minus 1 times a 3 to the n over 3 to the n plus 1. Using properties of exponents, this would be 5 to the n minus the quantity n minus 1 times 3 to the n minus the quantity n plus 1. N minus n plus 1, that would give me a 5 to the first, times a 3 to the n minus 1, 3 to the negative 1. And sure enough, we get back to 5/3. So that would be the formal proof that this sequence is geometric. You take the ratio of any two successive terms, and you get the same number, in this case 5/3. Okay? So write out the first few terms of the sequence. If it looks like you're multiplying the same thing each time, it's probably going to be geometric, and then that's the proof of it. Let's look at 8, b sub k, negative 1 to the k over 2k plus 1. Once again, this is something we had earlier today. So I won't go through the details again, but the b0 we got was 1. The b1 we got was, negative 1/3. b2 was positive 1/5. b3 was negative 1/7, and so on. So if you write these out, does it look like I'm multiplying by the same thing each time? Here the ratio is negative 1/3. Here the ratio is negative 3/5, so it's not geometric. Is it arithmetic? Am I adding the same thing each time? Here would be minus 1/3 minus 1 minus 4/3. 1/5 minus a negative 1/3. That's not negative 4/3. So this sequence is neither. All right, so if you try to take ratios, Negative 1/3 over 1 is negative 1/3. But 1/5 over negative 1/3, that's negative 3/5. So these don't match, so it's not geometric. And if we take differences, minus 1/3 minus 1 is negative 4/3. 1/5 minus negative 1/3 would be a fifth plus a third, which is not negative 4/3. So it's not arithmetic. So not arithmetic, not geometric means that it's neither arithmetic nor geometric. That being said, you can kind of see in the numerator, we're always multiplying by a negative 1, and then the denominator, we're always adding 2. So even though it itself is not one or the other, it's built up of arithmetic and geometric pieces, and that's what we'll talk about here in the next example. Okay. What about this next one? 2n minus 1, n goes from 1 to infinity. Oops. So once again, this was one we had earlier today. And when we wrote this out, we had 1, 3, 5, 7, etc. So geometric, the ratio is 3 over 1, 3, 5 over 3, 5/3. That doesn't work. But arithmetic works. If I take 3 minus 1, I get a 2. 5 minus 3, I get a 2. 7 minus 5, I get a 2. So it appears to be arithmetic. Now, how do I prove it's arithmetic? To prove it's arithmetic, I have to show that an plus 1 minus an is always the same number. That's how you prove it's arithmetic. So if I look at a sub n here is 2n minus 1. Then a sub n plus 1 would be 2 times the quantity, n plus 1 minus 1, which would be 2n plus 2 minus 1, which would be a 2n plus 1. And so if I take the common difference, or if I take the difference rather, of two generic terms, what happens? Don't forget to distribute the negative. Sure enough, the n's do cancel out, and I'm left with a positive 2. So that's the proof here that it is arithmetic. The common difference here is 2. Okay. So the way you check for geometric is you divide the successive terms. If you're getting the same number, it suggests it's geometric, and then you prove it by taking the ratio of the two generic terms. If you subtract adjacent terms and you're getting the same number, good chance it's arithmetic, and so you prove it's arithmetic by subtracting the two terms in general. If it's neither one nor the other, then it's neither one nor the other. I'll leave it to you on number 10. What appears to be happening here. Once again, they don't give us the whole thing. The numerator, let's see, let's write this out here. We can associate that negative wherever we need to. We'll put in the numerator. What's happening in the numerator as I go from one to the next? I'm always multiplying by negative 3. And what about the denominator here? I'm always multiplying by 2. So it appears to be geometric. with the ratio -3 in the numerator, 2 in the denominator. But there's no way I can actually prove it's geometric because I don't have the generic formula for it. You follow? So it appears to be geometric. If in fact it is, ratio would be -3/2. All right. And, we kind of spoiled it here. We got the formulas already. And so, once again, arithmetic sequences are linear functions with slope d. Geometric sequences are exponential functions with base r. So even though these look different, they're in fact the same concepts we had back in Chapter 1 and Chapter 6. So let's find an explicit formula for the nth term of the following sequences. So once again, we sort of have to assume that the pattern that we see is the same pattern that the author has in mind. And as long as your pattern is justified, they can't really get mad at you. But let's take a look at this first one. It's kind of curious. Number 11, 0.9, 0.09, 0.009, etc. So let's take a look at this. How am I going from one to the next here? Whoops. I mean, I'm just pushing another 0 in front of that 9. And if you remember with your arithmetic there, that's the same as we're dividing by 10 each time, right? So we're dividing by 10 each time. And dividing by 10 is the same as multiplying by what? 1/10. Or since we're in decimal land, 1/10 is 0.1. So it appears to be geometric. So that's telling whoever wrote this problem, I'm looking at it as a geometric sequence, and if that's the case, my formula a sub n is a times r to the n minus 1 for n bigger than or equal to 1. So a sub n is a, which is my first term, which is 0.9 times my r, 0.1 to the n minus 1. And this is good for n bigger than or equal to 1. So when you come up with a formula for a sequence, you need to have the formula, but you also need to tell me what value of n it works for. I'll leave this to you. There are infinitely many ways to write out sequences. Here's another formula that'll generate that same sequence. B sub k is 0.9 times 0.1 to the k power for k starting at 0. So you can shift things around. If you think back to Chapter 5 when we moved things left and right on the x-axis, you can shift things back and forth and have things start elsewhere. So we have a different formula, but because the b sub k starts at k equals 0, it'll generate the same list of numbers that the a sub n does starting at n equals 1. All right. So that's why the best way to check your answer is to write it out. Plug in n equals 1. You got 0.9 times 0.1 to the 0 power, that's 0.9. Plug in n equals 2. 0.9 times 0.1 to the first power, that's 0.09, etc. Okay? Let's look at number 12. We've got 2/5, 2, negative 2/3, negative 2/7, etc. Hint, write 2 as 2 over 1 and look for a pattern in the denominator. Okay. So let's rewrite this then as 2/5, 2 over 1. Let's put the negative in the denominator here because we're looking for a pattern in the denominator. Okay. And so if I look at the numerator is always 2, but let's look for the pattern in the denominator. Can we see a pattern in the denominator? So it appears I'm always subtracting 4 each time. And so in the denominator, it appears to be arithmetic. With the first term there being 5 and the common difference being a -4. So if I let, let's say, d sub n be the denominator sequence, it's going to be a plus n minus 1 d for n bigger than or equal to 1. So my denominator sequence would be a 5 plus n minus 1 times -4. And if I go through and work that out, I'd have a -4n plus 4 plus 5 plus 9. And so the pattern then for the sequence would be, well, the numerator is always 2, and the denominator would be -4n plus 9 for n bigger than or equal to 1. Oops. So even though the sequence itself wasn't arithmetic, and even though the sequence itself wasn't geometric, it had an arithmetic part to it. And once again, the best way to check your answer is to start with your formula and start plugging in those n's and write it out. Any questions on that example? Do you see how we kind of sort of broke it up into the parts? So the last one here, same thing. Got a hint here. Write 1 as 1 over 1 and look for sequence separate patterns in numerator and denominator. So if we rewrite this as a 1 over 1, and then we got a -2/7 and a 4/13 and a -8/19. Let's see what we've got here. It looks like in the denominator I'm seeing a pattern. So what's the pattern in the denominator? I'm always adding 6. If I look at the numerator here, what's happening? Looks like I'm always multiplying by 2. And if I want to associate the negative here with the numerators, I'm always multiplying by -2. So once again, this sequence isn't geometric. It isn't arithmetic, but it's built up of arithmetic and geometric. So I can get a sequence here for the numerators. So the numerators are AR to the n minus 1. The A here is 1. The ratio is -2 to the n minus 1 for n bigger than or equal to 1. The denominator sequence is a plus n minus 1d. So that would be a 1 plus n minus 1 times 6. So this would be a 6n minus 5 for n bigger than or equal to 1. I put these two things together to get my sequence, numerator over denominator, -2 to the n minus 1 over 6n minus 5 for n bigger than or equal to 1. And once again, the ultimate check. Start with n equals 1, plug it in, list out the terms. Okay. So other patterns that you should be on the lookout for here. Perfect powers. Like n squared, n cubed, etc. So be on the lookout for those. Like perfect squares would be 1, 4, 9, 16, etc. Okay, that's a common thing that'll show up in these sequences. And then the factorials, don't forget about them. They're going to come back strong next week. Factorials look like those. So those are some other patterns you see. They're neither geometric nor arithmetic, but they're patterns you want to be on the lookout for. Okay. There is no general way to come up with a sequence. In fact, there's a whole website that's dedicated to, if you just start typing in a sequence, it'll try to come up and try to match it for you. Okay, so you can spend all day coming up with sequences and plugging them into this website and seeing if it's a known sequence, if it's something known to math or something. By known to math, I mean something that someone's looked at and looks important and things like that. So there's that. Okay. So that's section 9.1. So we're not going to have anything for the rest of the week because of the Thanksgiving holiday. Originally, when this class was scheduled, it was Tuesday, Thursday. Well, there were two sections combined into one. They were Tuesday, Thursday, 8 to 10, and then 10 to noon. So this is why I have the live stream when I do. Next week, we're going to talk about adding up sequences on Tuesday. And then on Thursday, we're going to talk about the binomial theorem, which gives us a general way to multiply out things like x plus 2, like to the 5th power. Okay. So all of that comes together in that last section. Let's take a look at the take-homes we're working on. Take-home 13, that's the one due tomorrow. Let's take a look at this again. So number 1, put the equation in standard form and graph. So this is like what we did last Tuesday, a week ago. So if you want to check out the video there about how completing the square. The one thing I want to caution you about here is when you start this problem and get going on it, you've got to factor that -4 out of both of these y terms. Now, when you factor out a -4, you're going to be left with the y squared plus a 4y. Okay? And remember, whatever you then fill in to complete the square here, you've got to multiply it by -4 to put in over there. So don't forget to do that, because I've rigged everything to work out to be nice, friendly numbers. Okay? So that's a hint on that one. That's a common mistake on that one. Number 2, once again, this is like what we did last Tuesday. Remember, when you graph a function, you're graphing the equation y equals f of x. So you want to start off here, and then you want to square both sides. And then that's going to be part of a parabola. Which part of the, part of the hyperbola. Which part? Remember, you've got that negative there. And I want to stress, too, you can check your answers on Desmos. I expect you to be using Desmos there to double check to see how things are working. That'll also help you with the common mistakes. Number 3, sketch both equations. Once again, you can use Desmos to help you with this. And then solve the system algebraically. Okay, so I've had a couple of questions on this asking me, what technique am I supposed to use on this system? And the answer is, you can use whichever technique you like best. This is an example where you can do substitution or elimination. If you're going to do elimination, you're going to want to eliminate the x, because in the first equation and second equation there you have x to the 1st power. You're not going to be able to eliminate y because you've got different powers of y. So you can think about, so one way to get started on this, if you like elimination, is multiply that top equation by 2 and then add them together. That'll kill off the x. You'll be able to find the y's and plug the x's back in. So you can go do elimination that way. If you want substitution instead, then you could start solving. You could solve this equation for x and then plug it down into there. Okay, so I wanted to pick one where you could just pick whichever way you like to do the best. When you graph the equations in part A, graph them, and then just based on what you see, how many solutions do you expect? It's okay if you don't get the same number in part B. Part B, remember, you algebraically prove what you're getting or what you're not getting. Okay, A is just graph them. What do you expect to get? So it's always the algebra that proves what the geometry suggests on that. Okay, so that's 13. And let's look at 14 then. So this is what you'll be working on for next week. So we look at 14 here. And the first page is section 9.1. So this is all like what we did today. All right, so number 1, this is all section 9.1. So look at that. We're into December already. Where did the time go? All right. So write out the first 4 terms of the following sequences. Determine if they are arithmetic, geometric, or neither. Explain your reasoning. If the sequence is arithmetic, find the common difference. If it's geometric, find the common ratio. Okay? So you should be able to do all this by just writing out the first few terms. If you want to go the extra step and actually prove, like we did in class today, you'll get a couple extra bonus points if you actually go through and prove it. And then number 2, find an explicit formula for the nth term of the sequence. So you want to keep in mind, like what we did today, you can think of that 1 as a 1 over 1. And you might want to look at the numerators if that's a familiar sequence, and then the denominators if that's a familiar sequence. I guess it would help if I copied the sequence down correctly. All right? And once again, you're going to know you've got the right formula here because you'll just check your formula to see that it works out. And then number 3, this is actually kind of a callback. So you're going to notice on the next couple of take-homes, we're going to be taking you back earlier. So we got this situation here. We're planting a rectangular garden. And we're going to want to build a fence. So she wants the area of the garden to be 150 square feet. And so here's a sketch of the situation. So we need to have fencing along these 3 sides. We're going to call these sides the W and this side the L. We don't need any fence along the house. Okay. So we want 150 square feet. So that has to be the area of the garden. So how do you find the area? Well, you take the length times the width, and that has to be 150. Now, there's all kinds of different combinations of L's and W's that are going to give you 150. For example, let's do one of these here. If the width is 50 feet, then L times 50 would be 150, so the L would have to be 3 feet. You follow? And then how much fencing would I have at that point? Well, I'd have 50 plus 50 plus 3, so I'd have 100 plus 3, which is 103 feet of fencing. So what you're going to do here is fill in this chart. And as you fill in this chart, you're going to see, if you know what W is, how to find L, and then how to find the amount of fencing. So this will help you build a formula. So after you fill in that chart, you'll be able to say, well, how did I find L in terms of W? So if I knew what W is, how did I figure out L? So that's going to be one formula. How did you find the formula of the fence in terms of W and L? So this formula is just going to have W in it. This will have W and L in it. And then you can use these formulas together to get a formula with just W in it. And so that's your function. And then you're going to graph that on Desmos, and you want to find the minimum. Okay? So this is sort of it goes back, it's very much like the functions we looked at in chapter 3. So we actually did an example or two of this back in chapter 3 with the applications there. But you want to graph this on Desmos. So use a graphing utility. That's code for Desmos to graph your function and then find the minimum. Round your answers to the nearest foot. So the minimum amount of fence you need, and then what's the W and what's the L. So your graph will be a function here, y equals f of W, So on the points on your graph are going to have be the width and then the fencing, and then you can go for that. So it's a nice little modeling problem. Once again, it's not over the new sequence stuff. It kind of goes back a little ways, but it helps you start putting some of these pieces together. Okay. All right, so that'll do it.